And just looking into what we have with absolute value equations. Okay, so we have with number 90 in section R5, okay, we're looking at 4 times the absolute value of 2t plus 7 plus 2 is equal to 22. And again, we have, again, just for absolute value is going to be a non-negative quantity. And looking at what we have here, so I'm going to isolate the absolute value of 2t plus 7. Okay, so if I move the 2 upon subtracting, okay, so we have 4 times the absolute value of 2t plus 7 is equal to 20. And again, you do not treat the absolute value symbols as you would parentheses. So I'm not going to distribute 4 over all of 2t plus 7. So what I'm going to do here instead is to divide the equation by 4. And we have upon doing so, okay, so we got, again, with division by 4, okay, so we're going to have in the rewrite, we have the absolute value of 2t plus 7 is equal to 5, okay, and again, there'll be 2 numbers that will have an absolute value, say, equal to 5, and those would be like 5 and negative 5. And setting things up in terms of solving for t, which we have to be as part of the binomial 2t plus 7, once I remove the absolute value bars, okay, we have 2t plus 7 equal to those amounts with an absolute value of 5, one being 5 and the other negative 5. Okay, and so setting up our equations and solving for t. Okay, so I have 2t plus 7 is equal to negative 5. Also, we have 2t plus 7 is equal to 5. And taking what we have, okay, with this particular system, okay, so we have with the 2 equations. Okay, so we got a 2-step linear setup for each arrangement. Okay, so with 2t plus 7 equal to negative 5, I'm looking at taking 7 away from both sides. So we have 2t is equal to negative 12. And we have that, from this we have that t is equal to negative 6. Okay, and for 2t plus 7 equal to 5, if I take 7 away from both sides, again we have that 2t is equal to negative 2. And we're going to have, with division by 2, we'll have that t is equal to negative 1. Okay, so here we have that t is equal to negative 6, and also that t is equal to negative 1. Now for what we have in the case of the next item, okay, and we have for number 91, okay, and we have here, okay, now we're looking at the absolute value equation in terms of the variable c. So now we have negative 3 is equal to the negative of the absolute value of c minus 7, okay, followed by the addition of 1. And okay, so we have an absolute value expression on the right hand side of the equation, and if I get the negative of the absolute value of c minus 7 by itself, okay, so I can subtract 1 from both sides. So we have negative 3 minus 1, okay, so we have it negative 4. And we have that negative 4 is equal to the negative of the absolute value of c minus 7. And what I can do here is I can multiply or divide this equation by negative 1. Okay, And that's just to change the signs at both ends. And so for -4, that would be positive. The negative of the absolute value of c minus 7 is now going to be just the absolute value of c minus 7. And what I can do here, I'm just going to switch the order, have what is on the left to be on the right, and vice versa. Kind of like going from b is equal to A is equal to B format. Okay, so we have the absolute value of c minus 7 is equal to 4. And two amounts with an absolute value of 4 will be 4 and -4. And we're moving the absolute value bars. Okay, so c minus 7, it could be either 4 or -4. And so for what we have in the equations, we got at the lower end, we have c minus 7 is equal to -4. And at the upper, we have that c minus 7 is equal to 4. And so just looking at what we have now, okay, we're going to have for both equations the addition of 7 to both ends. Okay, so we got for c minus 7 equal to -4, and for c minus 7 equal to 4, we got -4 plus 7 is 3. And for c minus 7 equal to 4, adding 7 would come out to 11. All right. Now, for what we have in the next absolute value set, okay, and we have for number 93. Okay, so we got in this one, okay, so we're looking at solving this time for the variable y. Okay, so we got 2 is equal to 8 plus the absolute value of 11y plus 4. And I'm going to get this term by itself, so I can initiate the process upon subtracting 8 on both sides. Okay, so we've got 2 minus 8 is -6. And we have -6 is equal to the absolute value of 11y plus 4. And I can just switch the order. And something you might catch on. Okay, so we have 11y plus 4. Okay, we have that its absolute value is equal to -6. And so for what we have at this stage, okay, so for the absolute value of 11y plus 4 equal to -6, again, the absolute value of an expression cannot be negative. And because of the negative sign, okay, that means since the absolute value of an expression cannot be negative, okay, there will be no solution. And for what we have for the next situation, and we have crossing over to number 94, and this time we're looking at trying to solve for the variable z. And in this one, okay, so we have in the setup, okay, we got 6 is equal to 7 plus the absolute value of 9z minus 3. And getting the absolute value of 9z minus 3 by itself. Okay, so if I take 7 away from both sides, okay, so I have 6 minus 7 is equal to -1. And we have that -1 is equal to the absolute value of 9z minus 3. And again, I can just change the sides here, but you might already pick up, what has come to surface. For you have a bit of history from number 93 to crop up. Okay, and if you notice, you had the absolute value of an expression equal to a negative constant, which in this case of working with absolute value equations, again, is not allowed. So in this case, we're back to where we have no solution. Again, the absolute value of an expression cannot be negative. All right. Now, for what we have in the case of the next item, and this one is a little bit tricky, where you have an equation that has absolute value terms at both ends. And here we have the absolute value of 2a minus 3 on the left is said to be equal to the absolute value of a plus 2. Okay. All right, and let me give you just a little bit of a segue here. Like if I have like that. Say if I have like the absolute value of x okay, now terms that will have an absolute value of x so I have like the absolute value of positive x, that is equal to x. Absolute value of negative x is also equal to x. All right, and for what we have in the case of the layout, okay. All right, so for absolute value of 2a minus 3, okay, one is going to be 2a minus 3 itself. The other would be the opposite sign of 2a minus 3. Same thing for a plus 2. You will have a plus 2 with an absolute value of a plus 2. And also the opposite sign is going to be also with an absolute value of a plus 2. Okay, so what we have here, now we got plus minus plus minus. Now we have, one might be inclined to have like 4 equations set up where you have like positive, 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 negative, negative, positive, negative, negative. But the only thing I need is just a couple of equations. When we have like a pairing, let's say that we'll have like positive and a positive, and I need a pairing up where one expression is positive and the other is negative. So I'm going to keep 2a minus 3 on the positive side. And say that is equal to the positive of a plus 2. And where we have any negatives involved, so we have like the positive of 2a minus 3. Now take the negative of the quantity of a plus 2. Okay. So looking at what we have in the arrangement, okay, so I have 2a minus 3. Is equal to a plus 2. And I'll go ahead and solve for a. Okay, so you have like terms on opposite sides of the equation. Okay, so if I gather, say, the a terms, so we take away a from both sides. And here we have 2a minus a is going to be a. And we have a minus 3 is equal to 2. And we have one solution is going to be at 5. Okay. And for what we have in setting up things in the other equation, so I got 2a minus 3. And if I set equal to the opposite sign of a plus 2, okay, so we have negative a minus 2. And looking at combining variable terms. Okay, so I'm just going to move the a from the right, okay, by adding. And so I have 2a plus a is going to be 3a and I have 3a minus 3 is equal to negative 2. And we have with this equation, okay, so I have a two-step linear equation setup. Okay, so if I go ahead and add 3, okay, so I have 3a and minus 3 plus 3, that will go out. And negative 2 plus 3 comes out to 1. And we have with division by 3. Okay, so you have that a is equal to 1/3. Okay, and so for what we have for the solution set, okay, we have that a is equal to 5. And also we have that a is equal to 1/3. Okay, now for what we have in the case of the next items, okay, and we have in section R6, okay, we'll have what is going to be referred to as the complex number system. And the centerpiece of what we have for the complex number system, okay, that is going to be around a particular variable. Okay, so that's going to be the letter I. You have the I is equal to the square root of negative 1. And we're going to have the I squared is equal to negative 1. And just to kind of give you a view of what we have in terms of how complex numbers can be expressed. Okay, so let's say that if I'm looking at reducing in terms of the variable I, now let's say we have as a first instance here. Okay, see if I have the square root of negative 25. Okay, all right, now we got the negative of a perfect square value. And if I were to split up, okay, so you have like square root of 25 times the square root of negative 1. And the square root of 25 is going to be 5. And the square root of negative 1, that will go to I. And so the square root of negative 25 is equal to 5i. Let's say just another case here. If I have like the square root of negative 100, so I have the square root of 100 times the square root of negative 1. Square root of 100 is going to be 10. And again, the square root of negative square root of negative 1 becomes I. Okay, so we have 10i. All right, now let's say that if you have a run-in with an expression that is not a perfect square, okay, and we'll say that we have something like the square root of negative 28. Okay, so you have like the square root of 28 times the square root of negative 1. Now just work down. Okay, so the square root of 28, now the highest perfect square divisible into 28 is only going to be 4. And the square root of negative 1 is going to be I. And for what we have in the reduction, now the square root of 4 is 2. You have times the square root of 7 times I. And that can also be written as 2i times the square root of 7. All right. Now, let's say that where we have more than one term in a complex number. And this is going to be what is referred to as the standard form of a complex number. And for the standard form of a complex number, okay, that is going to be a plus bi. And now for the values of a and b, a could also be a negative quantity, b could also be a negative coefficient. And let's say that, and again, just maintaining what we have here. So we still got that I is equal to the square root of -1. And we still have that I squared is equal to -1. And let's say that if we're looking at simplifying expressions in standard form, and we'll say we have, first of all, we got 3 plus the square root of -49 and we have plus 7 minus the square root of -144. Now once we remove the parentheses, okay, which we'll get to in just a moment. Okay, so right now converting from the square roots of negatives to their equivalents in I. So square root of -49, that will be 7i. And for the square root of -144, okay, that is going to be 12i. And after writing the square roots of negatives as I terms, okay, and upon removing the parentheses, okay, so we have 3 plus 7i, and we have plus 7 minus 12i. And for what we have in the arrangement, okay, so you have just for the constants, we got 3 and 7, and you can go ahead and add those together. And for what we have in the variable I, we got 7i and -12i. And we have that 3 plus 7 is 10. 7i minus 12i is going to be a -5i. And guess what? We have the real coefficient at 10. And for the complex term in the letter I, we come out to -5i. Okay, so this will be the standard form of what we have after following through with the corresponding operations. All right, now, and let me mention, okay, again, just going back to what we have for single terms. Again, you have I is equal to the square root of -1. And we have I squared is equal to -1. Again, just for the standard form of a complex number. We have, once again, okay, we have a plus bi. Okay. And here's the rule of thumb, okay, just going back to working with single terms. Okay, whenever you're operating with complex radicals, like the square roots of negatives, what you can do is go ahead and write the radicals in terms of I. Now I'll show you why in just a moment. Okay, so we can go ahead and express each radical in terms of I. I'll give you just some cases here. Say if I'm looking at simplifying the following. Okay, and say if I'm looking at multiplying, let's say the square root of -9 and the square root of -4. Okay, so for the square root of -9 times the square root of -4. Okay, now for what we have in the mix, okay, so the square root of -9, this would be like the square root of -9 going to the square root of 9 times I. The square root of -4, this is the square root of 4 times I. Okay. And the square root of 9, okay, that is going to be 3. So the square root of -9, okay, is going to become 3I. Square root of 4 times I, okay, that's going to be 2I. And once we multiply, you got 3I times 2I. 3 times 2 is 6. And we got 6I squared. And guess what? We have I squared is equal to -1. So for 6I squared, okay, this will become 6 times -1. And for the product of the square root of -9 and the square root of -4, okay, this will come out to a -6. And that will be the result in this case. And let's say that let's say if you have at least a radical that is not the opposite sign of a perfect square value. And we'll say we have the square root of -20 times the square root of -5. Okay, so if I go ahead and write the radicals in terms of I, square root of -20 at the moment. Okay, so you have the square root of 20 times I. And for what we have in the case of the square root of -5, you will have the square root of 5 times I. And now, just for the rearrangement, okay, so got the square root of 20I times the square root of 5I. And, okay, now, neither 20 nor 5 will be perfect square values. But also, what I can do is that I can multiply together, okay, these radicals. So I got the square root of 20 times the square root of 5. And we have I squared. And looking at consolidating, so you got the square root of 20 times the square root of 5. And I can just multiply together. So you got the square root of 20 times 5. I can do it with positive values, but never do it with negatives. You always are going to draw out, again, the I. Okay, and I already did this in advance, and we have I squared is going to be -1. So I got square root of 20 times 5, so this will be square root of 100. And I squared is going to be -1. Square root of 100 is 10. And we have 10 times -1. And so that is going to end up at -10. So just a quick couple of cases that we have concerning multiplication. And now, let's say that in the case of division, let's give you one case here. If I have the square root of -54 divided by the square root of -6, and for the square root of 54 over the square root of -6, again, I'm going to draw out the letter I. So the square root of -54, that's going to be the square root of 54I. Square root of -6 will be the square root of 6 times I. I'm just going to write this again. Okay, so you have first order I terms factored out in both the numerator and denominator. Okay. And so for what I have here, okay, we'll have terms in I are going to cancel out. And for what we have in the follow through, okay, so you got the square root of 54 over the square root of 6. And there are various ways that you can go about factoring. Okay, you can say either the square root of 54/6, and we'll do it this way. So 6 would be divisible into 54. And again, between positives that we have the square roots of in a ratio, I can just make into the square root of the ratio of those positive values. So I got like the square root of 54 over 6. You can do it with positives, but never do it with negatives. And 54 over 6 comes out to 9. And we have in turn, okay, the square root of 9 comes out to 3. All right. And also, in looking at operating, say we have combining expressions. And we have as a fourth case, let's say if we're looking at the operation of addition as well as subtraction. Let's say we had the square root of -27 minus the square root of -300. And we have plus the square root of -48. Okay. So we're looking at a trio of negative radical terms to combine. Okay, so we got for this setup. Okay, so we got again, so you got the square root of -27 minus the square root of -300, and I can go ahead and draw out the letter I. Okay. All right. So looks like we don't have like radical terms, but if you look at simplifying or reducing, now for 27, not a perfect square, but it is the multiple of a perfect square greater than 1, and that number is going to be 9. So factoring out the square root of 27, that'll be the square root of 9 times the square root of 3. For 300, 300 is not a perfect square. but it is the multiple of 100, which is the highest perfect square divisible into it. So 300 factors out to 100 times 3. For the square root of 48, that can be factored out taking the highest perfect square. So you can see we have the square root of 16 times the square root of 3. Again, we have all these terms are in the letter I. So for the square root of 27i, this will become 3 times the square root of 3 times I. Next we have minus, subtraction. Here we have 10 times the square root of 3 times I. And then we have 4 times the square root of 3 times I. And if you notice, we have like radical terms that are complex. And you notice we have all these are square root of 3i terms. And if we combine the coefficients, so you got 3 minus 10 is -7. In turn, -7 plus 4 is going to be a -3. So we can say we have for the outcome, we can say we have -3 times the square root of 3i. And another way that you could express this is to have the I in front of the radical. So you can say either -3 times the square root of 3i or -3i times the square root of 3. Okay, now just going back to what we have with complex numbers in standard form. Okay, and now for what we have, say if I were to express in terms of a plus bi, let's see, we have just for first term here, let's say we have, kind of going back, let's say we have 3 plus the square root of -25. And we'll say we have minus 7 minus the square root of -81. Right. So if I were to express in terms of a plus bi, okay, so rewriting the square roots of negatives in terms of the letter I. Okay, now we have the square root of 25i, square root of 25 times I, so that would be 5i. And we got minus the quantity of 7 minus, and the square root of -81. Square root of -81 is going to be 9i. And here I can remove the parentheses. Okay, so you have 3 plus 5i. Removing the next group of parentheses, you're going to have 7 to be subtracted, and the -9i becomes plus 9i. And upon combining the constants, notice you have 3 minus 7 becomes -4, and we have 5i plus 9i, and this will become 14i. Okay, now, and let's say that if I have, let's say crossing over, let's say if we have multiplication. and say just like I just took the difference between these complex numbers. And let's say that if I had 3 plus 5i times the quantity of 7 minus 9i. Say if the multiplication happened to be the problem. Okay, so from day one, we looked at utilizing the FOIL method, and with complex numbers you still do the same thing, for this type of arrangement. So if I take the first product, we got 3 times 7 is 21. The outside product, 3 times negative 9i, we have a minus 27i. Inside product, we got 5i times 7, so it'll be 35i. And the last product, you got 5 times negative 9, so we have negative 45i squared. Okay, now you notice we're looking at trying to express in terms of a plus bi. Notice that the standard form does not have an I squared appearance. Okay, and again, just a reminder, for I squared is equal to negative 1, so I'm going to adjust this last term in a moment. Okay, so we got in continuing, so we got 21, now we got negative 27i plus 35i, and that is going to make a positive 8i. You got minus 45i squared, and again, I squared is going to be negative 1 and we have for the rewrite, so you got 21 plus 8i, negative 45 times negative 1 becomes positive 45, and 21 plus 45 will be 66. You have plus 8i, and that result is going to be the standard form. All right. Now, let's say that if you have what are going to be referred to as conjugates, and this would be like the complex number counterpart to like the difference of squares. So we have like 2 plus 3i times the quantity of 2 minus 3i. Okay, so if we take the FOIL, so we got 2 times 2 is 4, 2 times negative 3i is a negative 6i, 3i times 2 is going to be a positive 6i, we got 3i times negative 3i, okay, so this will be a negative 9i squared. Again, just to restate, again, we have I squared is equal to negative 1. So for what we have in setting things up, okay, if you notice, okay, we have a negative 6i and a positive 6i. So those terms are going to go out. And for negative 9i squared, we have negative 9i squared is that negative 1. And here we have 4. Negative 9 times negative 1 is going to translate to positive 9. And for the outcome here, we say that we have 4 plus 9 is 13. And if there were any other way to express this, since I don't have an I term with a natural number coefficient, since those negated, I could say 13, or if I had to give anything like in terms of explicitly A plus BI terms, but the only thing I could do really is say that I have 13 plus 0i. And I mentioned just a moment ago, okay, like with 2 plus 3i and 2 minus 3i, okay, those are what are referred to as conjugates. And so just taking what we have in terms of the purpose that they serve. Okay, so we have for the category of what we have with complex conjugates. Okay, and again, what would be referred to as conjugates. Okay, now, and we had a sample with 2 plus and 2 minus 3i. So you have like the conjugate of a plus bi is going to be a minus bi, and vice versa. Right, the conjugate of a minus bi is going to be a plus bi. And let's say that if I have like a complex number, and I'm looking at attaining the conjugate that corresponds. Okay, say if I have a complex number, so like have 3 plus 5i. Okay, so your a plus bi, a is at 3, bi is at 5i, and for a minus bi, the conjugate we have, notice the leading coefficient is going to remain fixed, and for the I terms, you're going to have opposite sign expressions. Okay, so you got 3 plus 5i and 3 minus 5i as conjugates. Now, let's say that if I have negative 2 plus 7i, notice in both conjugates, that which represents a will remain fixed. But again, any I terms will have additive inverses. So the conjugate of negative 2 plus 7i will be negative 2 minus 7i. Let's see if I have another case here. Let's say that if I have an expression of negative terms, say if I have negative 3 minus 10i, again, for both conjugates, or both conjugate expressions, okay, again, just the constants will be the same. But for the I terms, you're going to have opposite sign values. Okay, so the conjugate of negative 3 minus 10i, that is going to be negative 3 plus 10i. And here's one that might be a little bit tricky. Okay, see if I have like just the number 5. Okay, well 5 doesn't have an I alongside it. And you can think of this like 5 or 5 plus 0i, which is still going to be 5. Conjugate, well, a is referring, or 5 is referring to a. Conjugate, a remains unchanged. Okay, so like you envision like 5 plus 0i, 5 minus 0i, it still comes out to 5. And we can say that we have like the conjugate, let's say of negative 20i. So we don't have the explicit appearance of the representation of a, but we do have bi or negative bi represented by negative 20i. And as in the conjugate, you take the opposite sign of only the I terms. So with negative 20i as an I term, the conjugate is going to be positive 20i. And the product, okay, and working with conjugates. Whenever you multiply conjugate numbers, you're going to end up with a constant. Okay, and just sampling. Say if I have, say I have 7 minus 6i multiplied by the quantity of what is going to be 7 plus 6i. And if I multiply together, okay, so I have 7 times 7 is 49. Outside products, okay, we'll have it 42i. Inside product, we'll have it negative 42i. Last product got negative 6 times 6 is negative 36. And with the i's, we have negative 36i squared. Okay. And for what we have in the follow-through, okay, so you got 49. Notice we have 42i, and negative 42i will cancel. So now you've got 49 minus 36 I squared, and just serving as a reminder, again, I squared is going to be at negative 1. So here we're going to have 49, negative 36 times negative 1 is going to become positive 36. And 49 plus 36, okay, this will come out to 85. Also, for what we have, let's say just multiplying out conjugates, let's say we dealt with negative 20i, where the conjugate was 20i. And say if I multiply these together, now negative 20 times 20 will be negative 400. I times I becomes I squared. And I squared, again, that's going to be negative 1. And we have negative 400 times negative 1. And this will come out to 400. All right. Okay, so you got the product of conjugates. Now where they can come in, where the operation of division is concerned, see, we have complex number fractions. Okay, complex number fractions can be simplified by multiplying this is going to get a little bit wordy, but you have multiplying by 1 in the form of the conjugate of the denominator over itself. Okay, and just kind of taking what we have as a sample. See, if I express in terms of a plus bi, I'll say that we have as first case here. See, if I've got, we'll say that we have negative 2 plus 6i over 1 minus I. Okay, so got negative 2 plus 6i over 1 minus I. And where I have the taking what I have for the conjugate of the denominator over itself. Now the denominator we have a 1 minus I and if I multiply by 1 in the form of the conjugate of the denominator, now the denominator we have a 1 minus I, and the conjugate is going to be 1 plus I. And looking at what we have in distributing, okay, so just sorting together what we have now. Okay, so in the numerator, I have negative 2 plus 6i times the quantity of 1 plus I. Foiling out, so I got negative 2. Outside product have negative 2i. They have plus 6i. And again, we have 6i times I, so we have a plus 6i squared. And again, 6i squared is going to be 6 times negative 1. Now in the denominator, we have 1 times 1 is 1. We got plus I minus I. Again, we have conjugates involved. You have minus I squared. Again, we have positive and negative I to go out. And I'll do here, just bringing down what we have. Okay, so you got negative 2. Negative 2i plus 6i is going to make 4i. And you got 6i squared. And so we have 6 times negative 1 for 1 minus I squared. We have 1 minus negative 1 and for what we have in following through. So the numerator, we have negative 2 plus 4i 6 times negative 1 is negative 6. And 1 minus negative 1 would translate to 1 plus 1, which is 2. And for what we have in the numerator, so we got negative 2 minus 6 is negative 8. And we have plus 4i all over 2. And negative 8 halves is going to be 4. And 4i over 2 is going to be positive 2i. So we have in this reduction, okay, this is going to end up at 4 plus 2i. Okay. Now I'll admit this was kind of a lengthy process, okay, but this is what you have in the case of working with conjugates. And if we have, let's say, a complex fraction, I'm going to give one that is a bit more basic. So if I have just plain 3 over I, and I want to put this in terms of, let's say, its standard form. Okay, so you got 3 over I. And for what we're going to have in the case of taking what we have with 3 over I got the denominator at I. And if I multiply by the conjugate of the denominator, and the conjugate of the denominator is going to be negative I. Okay, so you got 3 times negative I is going to be negative 3i. You have over negative I squared. And the negative of I squared, remember, I squared is negative 1. And the opposite sign of negative 1 is going to be a positive 1. And so that is going to go to negative 3i. Okay, now just for the remaining portion, okay, we're going to go into some equations that will involve complex solutions. Okay, and we've dealt with items like quadratic equations, where we have like factoring by grouping, as well as using the quadratic formula. And for just samples of what we have here. Okay, so we got with equations that consist of complex solutions. And I'll give you just a few quick samples here. Okay, if I have, let's say, if I have something like x squared plus 4 is equal to 0. Now, I got a sum of squares, and in the case of working with squares, now, when we looked at something like x squared minus 4 is equal to 0, I could have used the zero product property if I were to factor to say x plus 2 and x minus 2. But with x squared plus 4 as a sum of squares and not a difference of squares, I cannot factor into real integer terms. Okay, so what I'm going to do here is that for x squared plus 4 is equal to 0, I'm going to separate the x squared apart from 4. And the result of, say, subtracting 4 from both ends, and we have the x squared is equal to negative 4. And if you notice, we have with the revisiting of the square root property of equality, like when we had x squared is equal to p, Okay, we have x equal to plus or minus, okay, the square root of p. And just on the same parallel, so you have p represented by -4, at least in the complex domain. And so we have that x is equal to plus or minus the square root of -4. And here we're going to have the x is equal to plus or minus 2i. So you have two complex numbered solutions with 2i as well as -2i. Also, if I have, let's say, an equation, I'll say we have something like x squared. I'll do it this way. Okay, so we have a leading coefficient. So we have 3x squared plus 5x. And I'll say that I have 3x squared plus 5x, and so I have plus 4 is equal to 0. All right. So for what I have here, I have a quadratic equation. Now the trinomial I cannot factor in terms of integer coefficients, but in terms of finding any solutions, I can revert to using the quadratic formula. And going with this route. Okay, so it's been a while since we looked at the quadratic formula, which you have x equal to -b plus or minus, okay, the square root of b squared minus 4ac all over 2a. And we have a direct substitution, so you got -5 plus or minus, and we have the square root, and again we have b squared is 5 squared minus 4ac is -4 times 3 times 4, and we have all over 2a, so we're going to have 2 times 3, and filling in what we have here. Okay, so we got -5. So we got -5 plus or minus. And for b squared, so we got 5 squared is 25. -4 times 3 is -12 times 4 is -48. Then we have all over 6. And as we narrow it down, okay, so we have -5 plus or minus. Now 25 minus 48 is a -23. And we have all over 6. Notice we had the square root of -23. Okay, so we got a complex number with -23. And we'll put this in terms of the letter I. So we have -5 plus or minus the square root of 23 times I all over 6. And if you draw out separately, and you can do it like in compact form, but say if I put this in standard complex number terms, so I have -5/6 plus the square root of 23 all over 6 times I, and with the a term for the other combination, we'll have -5/6 for a, and the other bi term is going to be the subtraction, where we have the negative of the square root of 23 all over 6 multiplied by I. Okay. And now I'll give you a little bit of a forerunner. Okay, and you'll have what will be referred to as equations quadratic in form. And I'll give kind of like the details, okay, next time we meet. But let me give you just a bit of a sample. If I have like x to the fourth, and we'll say we have plus 5x squared, and we'll say that we have minus 6 is equal to 0. Okay, so we have for x to the fourth, like just as x squared factors out to x and x, we're going to have for x to the fourth, this will factor out to x squared and itself. Now for negative 6, factors in negative 6 whose sum or difference will be on the plus side at 5. We have x squared plus 6 and x squared minus 1 factored, and I cannot factor x squared plus 6, and for x squared minus 1 I could factor that. Factoring is an option here for these types of equations, but I'll go ahead and factor to x plus 1 and x minus 1. And we have with the zero product property, say if I have x squared plus 6 equal to 0, and I take 6 away from both sides, I'm going to have that x squared is equal to negative 6. And with the square root property of equalities, I have x equal to plus or minus the square root of negative 6. And the square root of negative 6, we'll have the square root of 6i. So we're going to have a couple of complex solutions. We're going to have x equal to the square root of 6i, as well as the negative of the square root of 6 multiplied by I. And we have with the other factors, okay, so you have with x plus 1, so I have x plus 1 is equal to 0. And we have x is equal to negative 1. And we have with the other factor, okay, we have x minus 1 is equal to 0, whereupon we have that x is equal to 1. Okay, so for what we have in the mix, we have a couple of complex numbers and a couple of real values. So some equations you might have exclusively real values, and like in the first two examples, okay, you might have exclusively complex roots, but like in this last example, okay, we're going to have a mix of real and complex values.